Now students, for order of an element, let G star be a group with identity element E. A is any element, then its order is the smallest positive integer. It should be smallest, it should be positive, it should be integer. N such that A raised to power n is identity. If it make A identity when raised to power n, then order of A is n. It is also written as this. So this is the definition of order. Now we can conclude one thing from here, because G is a group, so closure property hold here. If we take A element from G and multiply A with A under this operation, so this resulting element must be of G. Then if we multiply it 3 times or we multiply it n times, let it be n times, then also the resulting element from the group. So if group is finite, here you can see this thing, if group is finite, then how can this all the powers of A square, A cube, A raised to power n and so on belongs to G? So there may be infinite element if we go on increasing the power of A, and all the powers are from G because G is closed. So we will discuss this in a theorem, in next theorem. Now this is the theorem. In a finite group, order of each element exists. So G is a finite group. Right? Now by closure property, if A is some element in G, then by closure property, the collection A square, A cube and so on, all the powers of A are elements of G. But G is finite because this collection is infinite. We can go on increasing the power of A. G is finite. Then what will be the property of this collection? That all the element cannot be different. Right? Therefore, all the elements, this collection, name it as S, elements of S cannot be different. Therefore, there exist some powers which are same for some I and J. You can say I and J are positive because all the power are positive integers, are positive integers. We can take, because these are two positive integers, we can have one greater than the other. Let I is greater than J. Right? Now, because all the powers are from G and G is a group and inverse of every element also exists in G, so A raised to power J is the element of G, then A raised to power minus J is also element of G because it is a group. In a group, inverse of every element exists. So we multiply both sides by A raised to power minus J. It will give us A raised to power I minus A is equal to A raised to power 0 is identity. So we get some power which make A is equal to identity, which is the definition of order if this is the least element. Because there is some element, there is some integer, because difference of two integer is again an integer. So we say that by ordering principle. Ordering principle is writing the integers according to their order. Like here we can see the simple example, minus 1 raised to power 2 is 1, minus 1 raised to power 4 is 1, minus 1 raised to power 6 is 1. So all these terms making minus 1 is equal to 1. By ordering principle we can write the least number at the first place and writing them in ascending order. So it is called well ordering or ordering principle. So by ordering principle, let m be the smallest integer, positive integer, such that a raised to power m is e. What is a? A is any arbitrary element. Arbitrary means randomly selected element from G. So if order of A exists, that means order of each element of G exists. What is the condition? That G must be finite. So the result is proof for a finite group, order of each element exists. Now see the next theorem, that G is a finite group and A is any element of G of order n. So order of A is given. Now we have to prove that A raised to power m is an entity if and only if n is divisor of m. So this is the if and only if condition. That means we have to prove this result both way. First taking A raised to power m is equal to identity and proving n is divisor of m. On the other hand, we take in a converse step, n is divisor of m, and then we will prove this result. So in two parts we will prove. Firstly, what we take, let order of A is n, it is given. Let for one thing we take, that A raised to power m is identity. So this we have taken. Now we will prove that n is divisor of m. Right? Now these are two integers. M is an integer, n is also an integer. So we use here division algorithm. So by division algorithm on m and n, what we do, we divide m by n, we will get some quotient and some remainder. This is division algorithm theorem. When we divide a number by the other number, we will have some quotient and then we will have some remainder here. So we can write m as divisor into quotient plus remainder, right? Now these q and r are also integers. Now and one more thing, the remainder must be less than the divisor 0 and greater than 0 or equal to 0, less than n. Now we can check this thing, that A raised to power m we have taken is equal to identity, but m is equal to this thing nq plus r. By writing this as nq and A raised to power r in product, now this is A raised to power n raised to power q into A raised to power r. A raised to power n, because n is order of A. Order means A raised to power n is identity. So this is identity raised to power q into A raised to power r. Identity raised to power anything is identity, and identity when multiplied with A raised to power r is A raised to power r. What we get from here is A raised to power r is identity, where r is less than n and greater than equal to 0, the remainder. So is it possible? Because the order of A is given to be n, so the least positive integer which make A identity is n. But here we get r which is less than n and it is making A identity. That means it is a contradiction, which is possible only if r is 0, because there is no other possibility r lying between 0 and n. So that will give us the order of A as r. Then order of A will be r, not n. So order of A is n. R is the number which is less than n, then r must be 0. If r is 0, then putting it here, m is equal to nq. What does it give us? M is a multiple of n, or we can say that n is a divisor of n. Therefore, m is a multiple of n, or n is a divisor of m. This proves the first part of the theorem. Now for the second part, let the other thing, that n is divisor of m, and what we will prove? We will prove a raised to power m is identity. The second part, it is called converse part. Conversely, right? Now what we will do, that we have taken n is a divisor of m, therefore there exists some integer, say q belongs to z, such that m is equal to nq, because n is divisor of m. That means this thing. Now a raised to power m is a raised to power nq, because m is nq. A raised to power n raised to power q, a raised to power n, because order of a is n, so a raised to power n is identity. So this is e raised to power q is e. So a raised to power m is equal to e. So that proves the converse part as well. Now the next very important result is this theorem, that G be a group and A be an element of order m in G. Then we have to prove that order of a raised to power k will be m upon GCD of mk, where k is any natural number and this bracket, round bracket mk, means GCD, means greatest common divisor of m and k. So to prove this result, what we are given is order of a, which is m, and what we have to prove, that order of a raised to power k is m upon GCD of mk, right? We have to take two things in this question. First, we will take the order of a raised to power k be t, that the order of a raised to power k be t, and GCD of mk, let it be t. GCD means greatest common divisor, the number that divide both the number. So it means d divides m. D divides m, this is a symbol of divide. D divides m means m can be written as some multiple of d, let m1 into d. And d divide the other number k means k can be written as multiple of d, let k1 d, such that m1 and k1 has GCD 1, right? So we can find two integers m1 and k1 such that their GCD is 1, and m can be written in this way and k can be written in this way. Now we come to the main proof that we need to prove is, we can write from here, we have to prove what? Order of a raised to power k, which we have taken t, is equal to m upon this mk we have taken as d. We have to prove t is equal to m upon d, or we can say t is equal to m upon d. From here, if we solve, taking d on the other side, it will be equal to m1. M upon d will be m1. So this is the result we will prove. So now we have come from this to t is equal to m1, the result we need to prove. And to prove two numbers, two integers equal, it is enough to prove that both divide each other. That means we will prove t divides m1 and m1 divides t. This is for you to remember. No need to write it here. This I have written here because to prove two numbers equal, we need to prove these two things. For proving these, firstly see that order of a raised to power k is equal to t means what is the order? Order means the power of that number which make it equal to identity. If the order of a raised to power k is t, that means a raised to power k raised to power t will be e. That means a raised to power kt is equal to e. But you can say now order of a is m. And from the last theorem we have seen the theorem, I remind it here. If order of a is n and a raised to power m is e, then order n divides m. This is what we have proven in the last theorem. So here the again the same thing is here, that order of a is m. There is another number which is making a is equal to e, that number is kt. That means order will divide that number because order is the smallest number. So any other number which make identity will be divisible by m, which implies m divides kt. Now the value of m is this one, m1d divides value of k is k1d, right, into t. So we put the value of m as m1d and k as k1d here. So now d cancel with d, therefore m1 divides k1t. But GCD of m1 and k1 is 1. GCD means greatest common divisor. There is nothing common in m1 and k1. That means m1 cannot divide k1. Therefore, what is left? m1 will divide t. That proves our one part. m1 divides t. We name it as number 1. Now consider a raised to power m1 into k, or you can write it like a raised to power k raised to power m1. So a raised to power k raised to power m1, we have to consider this step. It will be a raised to power m1k, and we are going to put here the value of k, which is k1d. This will be a raised to power, this is m1, so m1d into k, we attach d with m1. And what is m1d? m1d is m into k. This can be k1. It can be written as a raised to power m raised to power k1. A raised to power m, because a order of a is m, therefore a raised to power m will be e. E raised to power k1 means e. So again I am showing the same step here. A raised to power k is the number, b raised to power m1, then it is a raised to power m1k. We put the value of k as k1d from here, and we attach this d with m1. m1d is m, and a raised to power m is identity. So what does it mean? A raised to power k raised to power m1 is identity, but order of a raised to power k is t. We have taken this order as t. So order will divide any other number which is making that number identity. So this is the order t. Therefore t will divide the other number, that is m1. So this is our second thing, t divides m1. From 1 and 2, so what does it mean? That any number that is making some element identity is divisible by the order, because order is the smallest such number. So here also t divides m1, and from 1 and 2 m1 divides t and t divides m1 means both number, if they divide each other, means they are equal. That means t is equal to m1. Now you can write t is order of a raised to power k, and m1 is m upon d. And what is m upon d? It is m upon GCD of mk. Now see what happens if this mk is 1. now we consider if GCD of m and k is 1, then order of a raised to power k will be m upon 1. That means m, which is equal to order of a. So order of a raised to power k is equal to order of a if GCD of m and k is 1. That means the element and its any power will have the same order if the order of a and the power has GCD 1. Like if one number a has order p means it is a prime number, right? Then any of this power, a raised to power 2, a raised to power 3, order of a raised to power 4, all these numbers, all these elements have the same order, that is p, because p and any of this power p2, p3, all the numbers which will be 1, 2, 3 and so on will have GCD 1. So that means this is another important result, that a number and any of its power will have the same order if the order of that number is prime.